Hey, ladies and gentlemen, we're going to do 6.4 notes today on multiplying and adding probabilities. So, last section, let's jump to it. To find the probability of spinning a purple and then spinning a blue, you need to find the probabilities of both events occurring separately. So, I know that you can't tell the colors on your excuse me, picture. Let me share quickly the smartboard lesson with you so you can just look at those quick. Okay, so here is our diagram. So you might want to draw in the little white lines on your graph and then label like with a P, yeah, a Y for yellow, G for green, and so on. So we want to find the probability of spinning a purple and then spinning a blue. Excuse me. So spinning a purple is, and then a blue, they are independent. Whatever I spin on my first one is not going to affect what I spin on the second one. Oh, we almost had it. Okay, so I could sit here and try and spin the whole for a long time to see if I can get a purple and then a blue. All right, independent, doesn't affect each other. Oh, almost. All right, so let's jump back to our note sheet here. All right, so my stuff got bumped just ever so slightly. The probability of spinning a purple. So think back. So this was purple, was broken here, here, and here. So how many sections were purple? Well, one out of how many total? 1, 2, 3, 4, 5, 6 sections. Okay, and spinning a blue. This one was red, blue, blue, blue. So how many sections were blue? Well, 3 of them out of 4. Okay, so when we have an and a purple and a blue, okay, these are independent events. So in 2 independent events, we multiply. This should seem familiar. So I'm going to take 1/6 times 3/4. And remember, when you multiply fractions, you just multiply the top and the bottom. So we get 3/24. That I can reduce, and I can reduce it. 3 goes in to each of them, so 1/8. So the probability of spinning a purple and a blue is 1/8. Okay, so those are independent. Okay, so I want to know what's the probability of a purple or a blue. So in or statements, those are mutually exclusive. Okay, so it's when 2 events that can't happen at the same time. Okay, so I can't draw purple and a blue because they're on different things. So I just want to know for a purple or a blue. So these we're going to add. Okay, so a purple is still 1/6. Add, and a blue is still 3/4. Now to add fractions, remember we have to have common denominators. So 6 and 4, a good common denominator is going to be 12. So I'm going to multiply my first fraction, the top and the bottom, by 2. And I get 2/12 plus. Now in my second fraction, I have a bottom of 4. So I'm going to times it by 3. So this is just adding fractions. You did this late elementary, early middle school. So you get 9/12. Now, when you add fractions, just add the tops, keep the bottom the same. And we get 11/12. Okay, so it's much more likely to get a purple or a blue in this instead of just a purple and a blue. Okay, so independent events, they have no impact on each other. Mutually exclusive can't happen at the same time. So in this situation, we could have both of those. All right, so let's go ahead and talk about Julio. At a picnic, Julio reaches into an ice-filled cooler containing 8 regular soft drinks and 5 diet soda soft drinks. He removes the can and then decides he's not really thirsty and he puts it back. What's the probability that Julio and then the next person reach into the cooler and both randomly select a regular soft drink? Okay, the big thing here is it says Julio and the next person. So are these independent or mutually exclusive? Well, when it says and, it's independent. So we're going to multiply. Okay, so Julio we want to know about regular soft drinks. So how many regular soft drinks are there? There are 8. Over how many total soft drinks? Excuse me. There are 13. 8 plus 5. Okay, we said it's and, so we're going to multiply. And then the next person is coming, and they are going to also pick a regular soft drink. Now remember, Julio put his back, so there's still 8 to choose from. And there's still 13 total. So we're going to multiply. 8 times 8 is 64. And 13 times 13 gives us 169. Now, we always want to make sure that our fractions are as reduced as possible. So you remember you can just check that 16, oh, not 16, 64 divided by 169. Get it into a decimal on your calculator, but then don't forget you can push math, and the very first one is fraction, and it'll throw it back into the lowest common or lowest possible fraction. So 64 over 169 is the lowest fraction. All right. Excuse me. Let's try the next one. Okay. In a state lottery game, each of the 3 cages contain 10 balls. The balls are each labeled with 1 digit, 0 to 9. What's the probability that the first 2 balls drawn will be even and the third will be prime? Okay, so remember I focused on the word and. So that makes this independent. So we're going to multiply. All right. So 0 through 9, we want to know which will be even. Well, how many evens are there? So let's go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 2 is even, 4, 6, and 8. So let's see here. We're not going to count 0. Okay. 0 is not really even or odd. So 1, 2, 3, 4. Out of how many total digits? 0 through 9 is 10 total digits. It's an and, so we're multiplying. Okay, now the second ball, it's in a totally different cage, so this is what makes it independent. So we are going to be able to draw out of that second cage. There's still going to be 4 evens there out of 10. And then how many, the third will be prime. Do you guys remember what prime numbers are? Prime numbers are numbers that can only be multiplied by 1 and itself. Excuse me. So prime would be, I don't know if 0 considers prime. 1, 2, I'm going to circle them. 1, 2, 3, 5, 7. So we have 1, 2, 3, 4, 5 out of 10. All right, so multiplying fractions, we're going to multiply the top numbers. 4 times 4 times 5. And my trusty scientific calculator here. My graphing calculator battery's dying. So I get 80. And then 10 times 10 times 10. I have 1,000. All right, 80 over 1,000. That has to reduce. Okay, so did you reduce it on your calculator? Yeah, 2/25. All right, one teacher must be chosen to supervise the senior class fundraiser. There are 12 math teachers, 9 language arts teachers, 8 social studies, and 10 science teachers. If the teacher is chosen at random, what's the probability that the teacher is either a language arts teacher or a social studies teacher? Okay, so this is mutually exclusive because generally teachers just teach one subject. I know that we have some who have taught multiple subjects, but here in the section, in the problem, it just says you have math teachers, language arts, social studies, and science. It doesn't say anybody overlaps. Okay, so this is an or statement, so mutually exclusive. All right, so how many language arts teachers were there? 9. Over how many total teachers? So 12 plus 9 plus 8 plus 10. That gives us 39. It's or statement, so you're going to go ahead and add it. And then social studies teachers, 8 of them, over 39. Okay, so we're adding fractions. Excuse me. So you just add the top numbers and leave the bottom ones. So 8 plus 9 gives us 17 over 39. Both of those are odds. I'm guessing nothing simplifies out of that one. Actually, I know nothing does. So 17 over 39. All right, let's go ahead and go to the back side. All right, so probability. There are 7 girls and 6 boys in the junior class homecoming committee. A subcommittee of 4 people is being chosen at random and decides the theme for the class float. What's the probability that the subcommittee will have at least 2 girls? Okay, so is this independent or mutually exclusive? So it says at least 2 girls. So they could have 2 girls, they could have 3 girls, or they could have 4 girls because they have 4 on the committee. So this is a mutually exclusive. This is an or statement. So 2 girls or 3 girls or 4 girls. Okay, so this one, because we're taking multiples like this is actually a probability that we're going to include combinations for. So we have to have probability. Remember, that's successes over total possibilities. So we have to have a combination where we pick 2 girls. We have 7 girls to choose from, and we're going to pick 2. But there has to be 4 people on the committee. So if we're picking 2 girls, that means we also have to pick 2 boys. So we have to have a combination for those 2 boys. So we have 6 to choose from and 2 boys. Over, so that's the number of successes, over the number of possibilities. So that's total people on the committee, chosen from total members. So 7 and 6, so that's 13. And I'm going to choose 4. Okay, remember this is at least, this is an or statement. So I'm going to add. Now I'm going to, and this was for 2 girls and 2 boys. So this is going to be a kind of a little longer problem. So if you need to pause it to write, or if you need to rewind it and watch it a couple times, that's fine. Okay, so now we're going to say, hey, now we have 3 girls on our committee. Is there, or we have 3 girls. So we have 7 to choose from, and we're choosing 3. But if we choose 3 girls, we have to have 1 boy then. So there's 6 to choose from, and we're picking 1. So we had 13, and we're choosing 4, still the same. Excuse me. Plus, okay, now this is, oops, that should say 1 boy above it. So now here's our other statement, or we could have 4 girls and no boys. So we have 7 girls to choose from, and we're picking 4, times the probability of having 6 boys and choosing 0 of them, over, and still the same total. All right, so doing this, I'm going to show you using my scientific calculator. All right, so I'm just going to do 13, go to my probability, combination, choose 4. So I get 715. This is my denominator for all of them. So 715. Okay, so now remember, you can put these in at the same time on your calculator. 7, go over to combination, choose 2, times, I should put that in parentheses just to be on the safe side. 6, combination, choose 2. And I get 315. Okay, now I'm going to do the middle one. So 7, combination, choose 3. We're having 3 out of the 7 girls. And 6, combination, and 1 boy. I get 210. And then the last one, I have 7 girls to choose from, and I'm picking 4 from there. I have 6 boys to choose from, and I'm picking 0 of them. And we end up with 35. Okay, you're adding your fractions. So 315 plus 210 plus 35. Remember, when we are adding fractions, you don't do anything with the denominators. So you're adding 315, 210, and 35. And you get 560. So let's see if that reduces. 560 divided by 715. 112 over 143. Now I'm just going to show you guys. Oh, there's a little, there you go. If I hit enter, that gives me a 0.78. So that's a 78% chance that I'm going to have at least 2 girls on my committee. 2 girls or 3 girls or 4 girls. All right. Whew, that one was a long one. Not anything that's not difficult. It's just processing them. So let's just talk about dependent versus inclusive now. Dependent is when something affects the other one. So if you take a card and you don't put it back and you draw another card, what you picked for the first one is going to affect what you picked for the second one. That's a dependent. Okay. Inclusive is when they aren't mutually exclusive. So it's where it's kind of, okay, it says drawing a king or a spade from a deck of cards. Well, you can draw a king, you could draw a spade, but you also could draw a king of spades. So this is where you have an or statement, but you have something that could be both. So let's look at a couple of examples. Suppose that 1,400 students, 550 take Spanish, 700 take biology, and 400 take both of them. What's the probability that the student at random takes Spanish or biology? Now, excuse me, this one has that part right here. 400 take both of them. That's what makes this inclusive. So in inclusive, you're going to add the probabilities, but then you're going to subtract out that second piece, or that third piece, I should say, where it's the duplicate. So let's go ahead and look at this. How many take Spanish? Well, 550 take Spanish over the total. Now, plus, I'm going to add in how many take biology. There's 700 that take biology. But I have to subtract out those duplicates that are already counted in both Spanish and biology. So 400 take both of them. So remember, with adding and subtracting fractions, my denominator stays the same. So all you have to do is take your 550 plus your 700 minus your 400, and you get 850. Now go ahead and see if that can reduce. I'm sure it can. 850 divided by 1400. 17 over 28. All right, just a couple more, guys. 3 cards are drawn from a standard deck without replacing. That means you keep the card. Find the probability of drawing a heart, and a spade in that order. Excuse me. So here, you have talking about drawing hearts, and we're talking about drawing spades. They are not something that could be a heart and a spade. So this is not inclusive, but this is dependent. If I draw a heart and I don't put it back, that's going to affect how many hearts I can pick from for the second one. Okay, so this is a dependent problem. So if you don't remember anything about cards, look back at your 6.2 notes in the little rectangle on the back. We wrote down some key numbers for it. So how many hearts are in a deck? 13 over 52 total. Oops, we want to do times, sorry. Dependent is times. Okay, another heart. Now I have not 13 hearts, I only have 12 hearts. So I took one and I didn't put it back. That also affects how many total cards I have. I had 52, but I took one, so I no longer have 52, I have 51. Now we're talking about finding a spade. So how many hearts I had doesn't affect how many spades I have. So I still have 13 spades to choose from. But now I've taken 2 cards out, so I only have 50 left. So you multiply all the way across the top, multiply all the way across the bottom, or put them in parentheses and multiply them all at the same time. So 13 times 12 times 13, 2,028. And 52 times 51 times 50, 132,600. Okay, I'm sure that's going to reduce. They're both even numbers. So 2028 divided by 132,600. 13 over 850. All right. There are 2,400 subscribers to an internet service provider. Of these, 12,000 own brand A computers, 500 own B, and 100 own both of them. Okay. What is the probability that the subscriber selected at random owns either A or B? Automatically right there, when I hear something owns both or does both things, it's an inclusive. So brand A, how many people have brand A? 1,200 over your total. Then we we add, because it's an or statement, so we're going to add. How many had brand B? 500. Still out of the 2,400. Okay, but we had that own both of them. So I'm going to subtract that duplicate 100 out. Okay, because I'm adding and subtracting, all the bottom stays the same. So 1,200 plus 500 minus 100 is 1,600. So 1,600 divided by 2,400, and I get 2/3. So 2/3 of people are going to have brand A or B. All right, so find the probability of drawing 3 cards of the same suit without replacement. Perfect. If I know if they're coming from the same suit, they can't, there's no second choice here, so it's dependent. So it doesn't matter what suit it is, all of them have 13 out of 52. I pick one and I only have 12 left in that suit, and I have 51 cards left. I'm picking a third one. I have 11 over 50. So multiply your top numbers. 13 times 12 times 11, 17, 16, and 52 times 51 times 50. That's 132,600. All right. We're going to divide those. Oh, and it didn't want to pop it into a fraction for me, but don't worry, I've got it for you. 11 over 850. All right, there you go, ladies and gentlemen. Thanks for hanging with me. It's your last section of notes for this chapter. See ya.